Physics 2212, Lab 5, Magnetic Braking with Faraday's Law, by me, Grant Goding. The purpose of this lab was to collect observational data of a magnet falling through a conductive tube of aluminum foil, and to model the magnet / tube interaction computationally, and also to compare our computational predictions with the observed data. The physics principles involved here were the magnetic flux, which is this equation, which is the magnetic field through an area, or the magnetic field through a change in area, or the magnetic field could be changing, or the area could be changing. Faraday's law, which the EMF is related to the derivative of flux right here. Lenz's law is like an induced electric current will create a magnetic field opposite that of a changing magnetic field. Physics principles continued. Magnet falling through a ring will create an electric field. In the ring, the flux of the magnet through the ring is downward. Lenz's law, the induced magnetic field is upward opposite the flux. The induced current in the ring is counterclockwise. And it's like if your magnet's falling this way, its mu is this way too, the ring down here. That's what it's talking about. And the magnetic force is the current multiplied by the change in L across the magnetic field. In this experiment, we first determined the magnetic poles of the magnet, then the physical properties of the aluminum foil, then we recorded the magnet falling through the aluminum foil, then we measured the time it took for it to fall through, and then repeated it 5 times. Properties of the experiment: the magnet, mass of 0.034 kilograms, mu was 2.4 meters squared, aluminum foil roll, all its things right there. Some of the data. So here are my data after dropping. It's pretty quick to fall through the tube. So you can see it's like not long. The magnet, while falling through the aluminum foil, appeared to almost float. So like you could tell that the magnet was not necessarily floating, but it was slowing down as opposed to free falling. You could tell that there's a resistive force against this. And this was due to the upward force that the aluminum foil puts on the magnet due to the induced current on it. So, using glow script and our stuff, created the magnetic field and the flux in the ring that was here. Create a function to create the magnetic flux. I switched them. It's okay. Flux is up here. Create a function to create the flux and the magnetic field of the magnet, which was a dipole. In here, we created the magnet simulation as the magnet would fall through the tube. And here are our results. Doesn't show it much, but the magnet fell through the tube, and its time started here, and it stopped when it got to the bottom. And here's a graph of our velocity versus time. Finally, the conclusion. What if the resistivity of a conductor were reduced as close to 0 as possible? And how would the dynamics of the falling magnet change? Well, if we reduce the resistivity, the current would be able to be equal to that of the EMF produced by the falling magnet. So the current induced on the aluminum foil would increase because then, well, current and resistivity are inversely proportional. So reduce the resistivity, increase the current, simple math. And then the magnetic force would be greater, and the magnet would fall slower. And what if the holes were a slot that cut into the tube? How would this affect it? There'd be gaps in the rings, and so the magnetic field would be weaker because there would be less rings.